Hello student, I am Nirmala Morade, Assistant Professor, Department of Mathematics from S.V.K.T. College, Devali Camp, Nasik. In last lecture, we studied field axioms, that is field properties, as well as the number system. In today's lecture, we will study what is the definition of vector space and some simplest example of vector space. And when we say that a set is not a vector space, and some examples related to it. So, first we consider a non-empty set. Consider capital V is a non-empty set. We define two operations on V. First is addition and scalar multiplication or multiplication by a scalar. Addition is a rule which associates every ordered pair of two elements of V with a U plus V. That is, suppose U bar and V bar are the elements from V. These two elements are associated with the element U plus V. This is the sum of these two objects or the elements of V. Now, elements of V are known as either are known as vectors, and they are denoted by these symbols. For scalar multiplication, we consider one scalar and a vector. So, a scalar and a vector is related to a element k into U bar. It is called the scalar multiplication of U by V. So, this V is said to be vector space. V is said to be vector space if following properties are true. So, first property is U bar plus V bar belongs to V. This is the first property. So, here we consider U bar, V bar and W bar are the elements from V and take the scalars. K and L are the scalars. So, U bar plus V bar belongs to V, that is addition of two vector is again in V. It is also called as the vector addition or simply addition or the sum of two vectors. Second property is U plus V bar is equals to V plus U bar, that is vector addition is commutative. Third property is vector addition is associative, means U bar plus in bracket V bar plus W bar is same as U bar plus V bar plus W bar. So, this is the third property, vector addition is associative. Fourth property is there is an element or the object denoted by 0 bar in V such that 0 bar plus U bar is again equals to U bar. This element is called as the zero vector. This is called as a zero vector in V. The fifth property is existence of negative element. So, for any U bar in V, there exists another vector. So, we denote it by minus U bar is also in V such that if you add these two vectors, U bar and this is another vector minus U bar, their addition equals to a zero vector. Here minus U bar is called as the negative of U bar. Actually, these two elements are negative of each other. This is the fifth property. Observe all these fifth property are related to the vector addition. Now, next five properties are related to scalar multiplication. So, next sixth property is K into U bar again belongs to V, that is the scalar multiplication is closed in V. Seventh property is K times U bar plus V bar can be written as k times u bar plus k times v bar. Next one is the 8th property. K plus L times u bar can be written as k times u bar plus L times u bar. This is the 8th property. Now next one is the 9th property. K times L u bar can be written as k times L in bracket, k times in bracket L u bar, and the next, the 10th property is 1 times u bar equals to u bar. So these 6th to 10th, all these properties are related to scalar multiplication. So any non-empty set together with two operation, first one is addition and scalar multiplication, it satisfies all these 10 properties, then it is called a vector space. For the purpose of application, these scalars are taken from, these scalars are either real numbers or complex number. If the scalars are real numbers, then it is called the real vector space, and if the scalars are complex number, then it is called the complex vector space. So now we consider one simplest example of a vector space. All of you are familiar with the set of real numbers. So we consider here B is equals to R, that is set of real numbers. And we consider here scalars are also from R, that is all the scalars are also the real numbers. So you can easily check all these properties are true. If u bar, v bar, w bar are the real numbers, here v is equals to R, kl are also the real numbers, then we can easily check all these property, 10 properties. We know that addition of two real number is again a real number, then addition of real number is commutative, it is associative. We consider here, actually here we consider the addition is defined as addition of usual addition of real number and usual scalar multiplication of real number, that is multiplication of real number, and then we have to check all these properties here. So now we are here, addition of real number is associative also. So we know that if I consider any real number and we add 0 in it, answer is again the same real number, that is the 0 real number is the 0 vector of R. Similarly, if I take the 2 as a real number and we know that if I add its negation in it, that is minus 2 in it, the answer is again equals to 0. So here minus 2 is the negative vector of 2 in case of the set of real numbers. Also next, k is a real number, u bar is also a real number, their multiplication is again real number. Consider the 7th property. This is the distributive property for the real numbers, or it is true for all the real numbers. All these properties 7 to 10, we can easily check that all these properties are true for the real numbers. So the set of real number is a vector space over R, that is it is a vector space over itself. So if a set together with the two operations, it is a vector space if it satisfies all these 10 properties for all u, v, w belongs to v and k are the scalars. But if any one property is not true, it is a false, then we say that it is not a vector space. So consider the example, v is equals to R, that is set of real number, and now we consider the scalars are a complex number, that is we consider scalars, we take the scalars from as a complex number. Then what happen here? So we just check this 6th property here. So first is scalar is a complex number. So suppose I consider the scalar as 2 plus 3i, we know that it is a complex number, and consider one real number, say is 4, and do the multiplication. So answer is here 8 plus 12i, it is not the real number. It is not the real number. So we can say that the set of real number, if v is equals to R and scalars, we have to consider the scalars from C, then it is not a vector space. So R is not a vector space over C, but it is a vector space over R. So similarly we can check that this C is a vector space or do this problem at home. Consider the V is equals to set of complex number and take the scalars from R, that is the real number. We can easily check that it is a vector space. And suppose we want to prove that, or we want to check whether it is vector space or not. We want to check all these property. If any one property is not fulfilled, then it is not a vector space. So in next lecture we will study, in next lecture we will see the more vector spaces which are standard, that is R raised to n, particularly R square, R3 and so on, vector spaces of matrices, vector spaces of real valued functions and so on. Thank you. So let us consider the another example of a vector space. Let V is equals to R2, V is equals to R2, set of all xy such that xy belongs to R. We define two operations on it. First is vector addition and second is vector scalar multiplication. So for that, so we take two elements, u bar equals to x1 y1 and v bar equals to x2 y2 are the two elements from R2, and two scalars say k l belongs to R. Then define the addition of these two vectors as x1 plus x2 comma y1 plus y2. It is called component wise addition. For R2 is the set of ordered pair x comma y. So here we call S as a first component and Y as a second component. And here we consider the component wise addition, that is we add first component to the first component and second to the second. So x1 plus x2 gives the first component of addition and y1 plus y2 gives the second component of addition. Similarly, we define the scalar multiplication. K times u bar is equals to k times x1 comma y1 is same as k times x1 comma k times y1. Now also we consider the equality of two vectors when we say that the two vectors in R2 are equal. So here first vector is x1 y1. When I say that these two vectors, second vector x2 y2, these are two are equal, if and only if x1 is equals to x2 comma y1 equals to y2. So these three definitions are important. We take V is equals to R2, set of all ordered pair xy such that xy belongs to R. Addition of these two is a component multiplication. K times x1 be equal at this vector. R2 is a vector space with respect to addition and component wise. We get y1 plus y2, 1 x2 y1 number. So here That is, addition of these two vectors is plus V bar is so addition of these two. No, so this can be written as 2 equal. Now this ordered pair written by one. Addition of these two vectors, we use the U bar plus U bar, that is addition in R2 is commutative. Third property is association plus V bar in one bracket plus W bar. So for this property, actually we want to prove this one. So for this property, we required the third vector. So take W bar equals to x3 y3. Okay. Now starting with this one. So we consider U bar plus V bar plus W bar is same as U bar equals to, now just put the pairs, all these vectors in terms of pair. First is x1 y1, v2 is v is x2 y2 plus w is x3 y3, which is same as, okay, keep this pair as it is. First solve the bracket. So x1 y1 plus the addition of these two vectors is component wise addition. So we add these two first component. So x2 plus x3 comma y2 plus y3. Then again use the definition of addition. This can be written as x1 plus in bracket x2 plus x3 comma we add these two vector. So next component y1 in one bracket y2 plus y3. Okay. So all these numbers here, y's, x and y's are the real numbers and addition of real number is associative. So this can be written as, this first can be written as x1 plus x2 in one bracket plus x3. Do the same thing for the second one. So this can be written as y1 plus y2 in one bracket plus y3. So this is same as, again split this vector as an addition of two vector. The first vector is x1 plus x2 comma y1 plus y2 and the second vector is x3 comma y3. We split this addition as a addition of these two vectors. Again use the addition of u bar plus v bar. Again, so again this first vector can be written as addition of two vectors. So first vector is x1 y1 and the second vector is x2 y2. Okay, write this in one bracket and keep the third vector x3 y3 as it is. So this is same as, this is u bar plus this is v bar and this is a w bar. So here u bar plus v bar in plus w bar is same as u bar plus v bar is in one bracket plus the w bar. So the vector addition in R2 is also commutative, sorry, associative. So now go for the fourth property. So we keep this all definition as it is. Now our fourth property is, so for fourth property, if you remember the fourth property of vector space, there is exists a vector 0 in V such that 0 bar plus u bar is equals to again u bar, and this 0 bar is called as the 0 vector of the vector space. So now here first I consider u bar, which is equals to x1 y1. Now think about which ordered pair we have to added here so that output is again the u bar. Okay, we want to add some ordered pair here so that the answer is again a 0 vector. Again the same vector. So see here, u bar equals to x1 y1, and we want to find this second vector. We want to find this one such that answer is again u bar. So you can easily observe that if I put here 0 and add these two numbers, again answer is x1, and here y1 plus 0 answer is again 0. So here 0 comma 0, that is, so if I consider u bar plus 0 bar, that is equals to x1 y1 plus 0 comma 0, addition of these two vectors, x1 plus 0 is x1 and y1 plus 0 is y1, that is equals to u bar again. So for R2 with these two operations, the 0 vector is nothing but the ordered pair 0 comma 0, 0 comma 0. So remember this 0 vector for R2. Next fifth property is existence of negative element. So u bar is in V, we want to find minus u bar in V such that if u bar is in V, we want to find minus u bar in V such that their addition equals to 0 bar. So minus u bar is called the negative of u bar and vice versa. So now our u bar is equals to here x1 y1. This is our u bar. I want to a vector here such that answer is 0 0. So we want to find this vector, this pair such that answer is equals to 0 0. So logic is clear here. If I put here minus x1 minus y1, and if we add these, we will get the 0 0 answer. Okay. So now here u bar equals to x1 y1 minus u bar equals to minus x1 minus y1. Now add these two vectors, u bar plus minus u bar is equals to component wise addition, x1 minus x1, x1 plus minus x1, comma, add the second component y1 plus minus y1, so which is same as x1 minus x1 is 0, y1 minus y1 is 0, which is equals to 0 vector. So here minus u bar, that is minus x1 y1, is the negative of x1 y1. Remember this one. What is the negative of x1 y1 in R2? It's minus x1 minus y1. That is, suppose 2 3 is a vector, its negative is minus 2 minus 3. When we add these two, answer is a 0 vector again, that is the ordered pair 0 0. So this is our fifth property. Now next property is the sixth one is. Sixth property is we want to prove that a scalar into a vector u bar is again in V, that is again in R2. This is we want to prove here. So if you consider k into u bar, this is our definition. K into u bar equals to k x1 y1, which is equals to k x1 y1. So if k is a real number, x1 y1 is also, both are real numbers. So we know that addition of two real number, multiplication of two real number, even though subtraction of two real number is again a real number. So these two are real numbers. So the ordered pair of two real numbers belongs to R2. So this is obviously true. So the scalar multiplication is closed in R2. Now next property is the seventh one. We want to prove that K times U plus V bar is same as KU bar plus KV bar. Now we want to prove this one. So starting with this one. So now we consider K times U plus V bar, which is same as, keep the K as it is. Now put the value of U bar plus V bar, addition of these two vector, which is same as x1 plus x2 comma y1 plus y2. That is, we add these two vector. Now next use the second definition, scalar multiplication, component wise scalar multiplication. K times x1 comma y1 can be written as K times x1 comma K times y1. So just remember, we multiply these two numbers by K. So according to this definition, this can be written as K times x1 plus x2 comma K times y1 plus y2. Now solve this one. So this can be written as, all these are real numbers, so use the distributive property. So by distributive property, this can be written as kx1 plus kx2 comma ky1 plus ky2. So just rewrite this one. So this can be written as, I write the left hand side as it is, K times U bar plus V bar is equals to, now continue with this one. Now this addition can be written as, or this vector can be written as addition of two vectors, because we are interested in this thing, K times U bar plus K times V bar. So this vector can be split as addition of two vector. The first vector is kx1, ky1. And the second vector can be written as, first vector is kx1 comma ky1 and the second vector is kx2 comma ky2. Here k is remaining, ky2. Okay, again use the reverse definition. This is nothing but ku bar, kx1 comma ky1 is equals to ku bar, and this is equals to k V bar. So thus this property is also true. K times U plus V bar equals to KL plus KV. Now our next, that is 8 properties. We want to prove that K plus L times U bar is equals to KU bar plus LU bar. We want to prove this one. So for that, starting with this one, so we consider here K plus L times U bar is equals to K plus L, keep as it is, put the value of U bar, which is x1 y1. Now use the definition of scalar multiplication. As a K is a scalar, L is scalar, the addition is again a scalar. So treat this as a whole scalar, and now use the definition of scalar multiplication, that is the second definition. Okay. So using this definition, this can be written as K plus L x1 comma K plus L y1. Okay. Now try to write this in this form, because we want to prove this one. Separate the term of K and separate the term of L here. So this can be written as, first I have to solve this. So since these are real numbers, this can be written as K times x1 plus L times L1. We use the distributive property here, K times y1 plus L times y1, by using the distributive property of real numbers. Okay. So now let us continue this. So this is same as, so write this vector as addition of two vector again. So now it is easy to write. So this is same as the first vector whose components are kx1, ky1. So this forms a first vector and this gives the second vector. So this is addition of these two vectors. This is first vector and this is second vector. So second vector is plus Lx1 Ly1. And we know that kx1 ky1, x1 y1 is nothing but u. So this is equals to ku bar and this is a lu bar. So our property is true here. K plus L times u bar equals to K times u bar plus L times u bar. This is our 8th property. Now concentrate on next property, that is 9th property. So first write what is the 9th property and try to prove it. So our 9th property is Kl times u bar can be written as K times Lu bar. K times Lu bar. So we want to prove this one. So starting with this, Kl u bar is equals to, keep this Kl as it is and put the value of u bar which is x1 y1. Now use the definition of scalar multiplication. So this can be written as Kl x1 Kl y1, because we know that if K and L both are the scalars, so K into L is again a scalar. So use the definition of scalar multiplication, that is this definition. So we get here. So all these are the real numbers, all the numbers present here, K, L, x1, y1, all the real numbers. So use the property of real number. Matrix multiplication is associative, not a matrix multiplication. Multiplication of real number is associative. So this can be written as K times Lx1, comma K times Ly1. So this can be written as K times Lx1 and K times L times y1. So we use the reverse definition of scalar multiplication. Kx1 ky1 can be written as K times x1 y1. Use the reverse definition here. So this can be written as K times Lx1 Ly1. So which is same as K as it is, and this is Lu bar. This is Lu bar, and thus the property is true here. This is our 9th property. And now last, that is the 10th property, which is the easiest one. We state first the 10th property here and then prove it. So our last 10 properties, prove that 1 into u bar equals to u bar. So here 1 is a unit element or here real number. So 1 into u bar which is equals to 1 into x1 y1. 1 is a scalar here. Use this definition. K times x1 y1 is K times x1 comma K times y1. So this is 1 times x1, 1 times y1. 1 is real number, x1 y1 also real number. So this can be written as x1 y1, that is equals to u bar. So this is our the last property. So now here we consider V equals to R2, that is the set of all ordered pair xy such that xy belongs to R, that is their real number. We define the addition in this form. We define the addition of x1 y1 x2 plus x2 y2 as x1 plus y2, x1 plus x2 comma y1 plus y2, that is component wise addition, and the component wise scalar multiplication K times x1 y1 equals to K times x1 K times y1. So under these two operations, addition and scalar multiplication, we call this as a component wise addition and component wise scalar multiplication. R2 is a vector space over R. R means set of real numbers. So similarly you can just extend the same concept for R3. What is R3? R3 is nothing but the set of all triplets xyz such that xyz belongs to R. So we can easily prove that R3, R raised to 4, R raised to n are also vector spaces or with component wise addition and component wise scalar multiplication. Next lecture we will study the examples of more vector spaces. We generalize R2, that is vector space R3, R raised to 4, R raised to n, vector space of matrices, vector space of real valued functions and so on. Thank you.